I'm going to talk about the shift-driven long-lived turbulence from magnetic buoyancy. It is the result of a little more than 2 months of research I had to do with my school Polytechnique, and I did with Zika here. This internship was during the first year of master, so I will still have to study after that when I come back to France. First, it had to be called magnetic buoyancy in the solar dynamo, but as we are not sure enough that there are really dynamo in what I studied, we changed the title. So here is the outline of my talk. First, I will talk about the theory, the different equations and physics which are involved in this physics situation. Then I will talk about the simulations I did, and then a few results I will have to present you. First of all, the theory. The magnetic dynamo is a conversion of the kinetic energy into magnetic energy. It means it must be always creating new magnetic energy because there is a dissipation. And this magnetic energy comes from the kinetic energy, so it means we have to have a source of kinetic energy. So the most important equation is the equation of induction, which links the temporal evolution of the magnetic field to a term due to which involves kinetic and magnetic fields, and then there is a term of dissipation. So this is a non-approximative law which comes from these 4 equations. Then we are interested in that because in the sun there is a magnetic field which is important. It is still not very understood how it works because all the simulations now can't reproduce the observations that are done in the observatories. So we are going to try to find another way of explaining the magnetic dynamo in the sun. We are interested in the main field because we know that there is a strong main field developing in the sun, and so we are interested in the main field equation. So it's basically the same equation as the induction equation, but there is a new term which comes from turbulence, from the kinetic and the magnetic turbulence. So it means that we are going to need some turbulence, because if we don't have this term, this equation is linear with B, and there could be no real increase of B. So this term will matter very much. Then, during my internship, I worked with simulations which had a linear shear. First of all, it was for physical reasons, because in the sun there is presence of a shear in a place called tetocline. So it may be really relevant to explain the magnetic dynamo. So in the simulation, I used a linear shear in a Cartesian box. So if, for instance, it's not the case of the sun, which would be in spherical coordinates, but here we would have something like UR, U theta, and U phi, like that. And here we have our Z, the shear, the difference of the, we put in my simulation UI equal to S times X, and we know that the field is different along the U theta axis, so this was equivalent to the UX, so R theta phi would correspond to something like that, because we had a gravity in the Z direction. So it is to have a Cartesian box. And then what does this sphere really do? First of all, it will allow the omega effect, which makes that if there is a magnetic field in the x direction, it will be converted into a field in the y direction. Then I'm going to talk about the magnetic buoyancy. Magnetic buoyancy is real easy to understand. Everybody knows that if there is a magnetic field, there is a magnetic pressure expressed as v squared over 2 mu naught. And as the pressure must be always the same, then it means that if there is a place where there is a magnetic field near one where there is no magnetic field, the pressure must be the same, and the pressure is the sum of the thermal pressure and the magnetic thermal pressure and the magnetic pressure. So if there is a strong magnetic field, this term will increase. This one will always be the same. So this one has to decrease. And if the thermal pressure decreases, it means that the density will also decrease, and there will be a buoyant force. The acceleration will be like this. So I did the simulations with the pencil code that everybody knows here. It's an exact code with 6 order in space and 3rd in time. And all the simulations I will present were done on 64 mesh points cube, and they were done on a PDC computer. The first problem I had, and it was the main part of my whole internship, was to find the good boundary conditions. Because there were many problems. First problem I had at the beginning was that the entropy swap did reverse on my simulations. So we know that we have to have an entropy swap like that if we have Z here, and the swap it must be like that. Entropy will increase with Z, so that there is the gas is totally stratified. And in my simulations, after a certain time, sometimes I had something like that, which would mean that here there would be some convection, which I didn't want, because if there is convection, then there will be a force motion, and there would be no possible way to know what comes from magnetic buoyancy and what comes from convection. The second problem is that, of course, I wanted something like a dynamo, so that the magnetic field should increase. So here are the different boundary conditions I could use. Either I could decide that the entropy could vanish at the top or at the bottom. This can be good because the entropy is something relative in the pencil cut. So it just means that we fix the entropy at one boundary. Then there was another boundary condition, which was much more free, because it just said that the second derivative vanishes, so the entropy can take any value. And then there were some more physical boundary conditions, which impose either that the radiative flux is fixed, or that the temperature is fixed. And of course, we could mix all these boundary conditions to have different ones at the top and at the bottom. So here are the files I had in the pencil code to do the simulations. So in the cprogram.local file, I just wanted 8 processors on the PDC computer and 64 mesh points. Here are the physics I had to use. These are all basic physics, and this one is not so used, so it was the originality of my internship here. Then during the simulations, most of the simulations I did all the simulations I did were done with a shear equal to -0.1. Then I had a gravity profile constant to make things easier, and I took a polytropic gas of polytropic stratification at the beginning with an index of 1.6, which means that it was fully stratified at the beginning, as the index was more than 1.5. And then So here was the problem of the boundary condition, so it moved a lot. And in the simulations I'm going to talk about, I always had heat heat conductivity of 0.1, a magnetic diffusivity of 5 10 minus 4, and a viscosity of 2 10 minus 3. So first, the magnetic fields we can show here in some simulations. That is the boundary conditions at the bottom, and that is the boundary condition at the top. We can see that first, these are the magnetic field squared, the mean magnetic field squared, and this is time. So first of all, we have to think about the characteristic time scales. In the last slide, I showed you the values of the different diffusivity and conductivity, and it means that our biggest time scale was something like 2000. It was due to the magnetic diffusivity, and here we're running this simulation for a time of 8,000, and this one for a time of 5,000, so it's more than the time scale. So we have to notice that first there is a very big increase during something of the order of the time scale, just less than that. Then there is a decrease, and again a bigger decrease, because before it becomes very steady. We can also see that in these two, with those different boundary conditions, there is a meaningful difference of values, because this one goes almost at 0.06, and this one is just 2/3 of it. Then with other boundary conditions, we still have the same shape, but we can see that the first time is very shorter than the time scale of diffusivity, of magnetic diffusivity, but there is still at the end something like something which is very steady. Then here are the profiles of density, time speed, and stability of the stratification after a certain time for two different simulations. In a dash line, it was done for C1 boundary conditions, so constant flux at the bottom and fixed temperature at the top. And in the continuous line, it was done for A2, so it was a slope of entropy which was constant. We can see that there is no real difference at for the density, except at the very top of the box. But there is a very big difference for the sun speed. Here in this one, as the temperature is fixed at the top of the box, the sun speed has to be 1 at the top. So it's like that at the beginning, and it will stay like that until the end. On the other side, if there is no constraint about the sun speed, it can evolve, and here we can see that it goes very up, and it becomes more homogeneous, which means that the simulation is almost isothermal. Then we can see the stability of the stratification, which is known thanks to the nabla. And we can see here that the two are still stratified because their value is under 0, but one is really more stratified than this other one. Here is the velocity field at the very beginning of the simulation when I had no shear. So there was just a horizontal tube of flux centered at around z equal -3 at the beginning, and then that was all what happened. We can see that there is almost no velocity in the x direction and y direction, but in the z direction there is a lot of movement. That's 10 power minus 3. So that's still more than this value. And first of all, we could think that there were sound waves because the frequency is something like between 1 and 2 time steps, and this corresponds to the sound waves frequency. But on the other side, if there were sound waves, it would mean that there would be no real motion And we know that there is real motion because things are going up thanks to magnetic buoyancy. So we don't really know what these are now. Then we can compare the case without shear with the case of C1 boundary condition.